Take it away.
All right. Hello, everyone. And thanks to Mark, Peter, and Ryan for giving me the opportunity to present our results on robust polarimetry via convex optimization. So here is the outline of what I want to tell you today. So first, I will introduce polarimetry and polarization and try to tie it in with quantum information science. And so next I will show you the experimental setup that we use for polarimetry. And more importantly, hopefully you'll be able to see the motivation behind this project from the specific experimental methods. And third, I will show you how we construct convex optimization problems for polarimetry. And then I'll show you the results that we obtained. And finally, I will compare our method with previously proposed methods. So first of all, polarimetry is the measurement of polarization. And what polarization does is polarization describes the trajectory of the electric field vector of light as it oscillates. The Stokes parameters describe the state of polarization, and they're defined here. So the P's here are the intensity of light after it passes through a polarizer corresponding to the subscripts here. So H and V are horizontal and vertical, D and A are diagonal, anti-diagonal, R and L are right and left circular polarizations. And the S naught is just the total intensity of the light. The Stokes parameters, we can write them in the form of a coherency matrix, which is Hermitian and positive semi-definite by construction. So this form should be familiar to everyone here because it's equivalent to a density matrix of a qubit. So which means, for example, if you're doing quantum state tomography on a polarization qubit, you're effectively measuring the Stokes parameters. So another important thing that we want to know when we're talking about polarization is the degree of polarization. So the physical meaning of the DOP is that it represents the ratio of the polarized portion of light to the total intensity. And it's actually proportional to the purity trace J squared or trace rho squared of the coherency matrix. Now there is a subtle difference here. The DOP is in the range of 0 to 1 because it's a ratio of the polarized light to the total light instead of the range of the purity, which is from 1/2 to 1. So accurate measurement of the state of polarization is crucial in any technology involving the polarization of light. So what we are presenting here is a mathematical method based on convex optimization for correcting non-physical polarimetry results caused by experimental errors. So what we mean by non-physical is that there are negative eigenvalues in the coherency matrix that are caused by errors, should not happen, that are obviously not physical. The negative eigenvalues will cause the degree of polarization and the purity to be greater than 1, right? That doesn't mean anything, right? So the coherency matrix can be written in the Pauli basis, and it can be represented geometrically in a sphere in the exact same fashion as the block sphere, except that for polarization, this is called the Poincare sphere. Now there are subtle differences between the Poincare sphere and the block sphere in the orientation, which you can see from the order and the sign of the Pauli matrices in equation 5. And this causes the 0 and 1 state to be on the equator. The 0 and 1 are the horizontal and vertical states. They're on the equator instead of on the poles. But this difference is purely due to convention. Mathematically, they're equivalent. So as we all know, optics is widely used for the research of quantum sciences. For example, the very first Bell test was done with polarization qubits. But here we want to do the opposite. So the results that I'm presenting today is part of a larger effort of importing techniques and methods from quantum information sciences to optics. So specifically, convex optimization has been used for quantum state tomography to reduce the effect of experimental errors. So we want to show similar methods can be used for polarimetry. All right, so before continuing to the optimization methods, let's look at the experimental setups. So we used the two setups shown here to measure the state of polarization. All right, so in both setups, first the source laser is vertically polarized, and it passes through either a half-wave plate or a quarter-wave plate to change the state of polarization. So the half-wave plate will rotate the angle of polarization while keeping the linearity. So it still will be linear polarized, but the angle will change. But the quarter wave plate will change the linear polarization to an elliptical polarization. And in figure A, the detection is done with what we consider the standard polarimetry method, and the detection scheme consists of a quarter wave plate, a linear polarizer, and an intensity detector. So we use 4 intensity measurements to reconstruct the coherency matrix, and using the equation to the right. So the I psi phi is the intensity measured when the quarter wave plate is at angle psi and the polarizer is at angle phi. So for this setup, the obvious experimental errors are the fluctuation of the laser intensity between the 4 measurements, and also there's some error in determining the angle of the waveplate and the polarizer. Right, so setup B is simpler, where we use a polarimeter to measure the state of polarization directly. So the polarimeter is a commercial device that does what's shown in the dash box in A. So it has the quarter and the polarizer inside a black box. And it's relatively expensive. It's supposed to be fast, so with a sampling rate of more than 50 hertz, but it's not perfect. So there are problems that we saw when we used the polarimeter. Problems that causes the measurement result to be non-physical. So first of all, like with high intensity, this is something that we noticed very early on, is that when the polarimeter is measuring high intensity light, the state of polarization is not accurate. So we had multiple back and forth with the technical support on this, and they've actually changed the specification of the polarimeter to say that the polarimetric measurements are only guaranteed for intensities lower than 2 milliwatt. So it is definitely not perfect. If we consider the setup in B and what we can actually do to reduce errors, because it's so simple, there's not that much we can do. So if, for example, the polarimeter gives us a degree of polarization of 1.1, the only thing that we can do is we can check the alignment between from the laser source to the half-wave plate to the polarimeter, and that's it. If the polarimeter is still giving us a non-physical result, there's nothing else we can do. And those physical results might be caused by misalignment of the internal components of the polarimeter. So, and there have been multiple experimental methods to fix such experimental errors, such as pre-calibration of components, or using a feedback scheme of some sort, or using a completely different detection scheme. But you can imagine those methods will not work in setup B with just a single polarimeter. So that is the main motivation for this project. We want to find a method that can be applied in post-processing and is independent of the specific experimental setup. So the method that we are going to use is convex optimization. First, we want to find the optimization problem that has this goal, which is to find the corrected coherency matrix that is closest to the measured coherency matrix under the constraint that the corrected one be physical. So that is equivalent to this optimization problem, where we minimize the norm of the difference between the two matrices while keeping the corrected matrix physical. So for an optimization problem to be convex, the objective and constraint functions have to satisfy this condition in equation 17. So we can go back and check. So 16A is convex due to the definition of matrix norms. And 16B is convex because the set of all density, all positive semi-definite matrices form a convex set. And 16C is also convex just due to the linearity of the trace. So our optimization problem is a convex optimization problem, and that guarantees that the solution is unique. Now, the reason that we did not specify which matrix norm to use is that this method should work for any matrix norm, and we will compare different norms in later slides. So next, we also constructed optimization problem to find the coherency matrices corresponding to the highest and lowest degree of polarization given some tolerance. So to illustrate this, I drew this figure here. So we want to parameterize a ray going from the origin of the Poincare sphere in the direction of the measured Stokes vector. And that is done by equation 18 here. And so once we have this picture in mind, then the problem, the construction of the optimization problem is pretty simple. So to determine Jmin and Jmax, we just have to solve these two optimization problems. And for similar reasons as before, these two problems are all convex. So here are the experimental measured and corrected results. So first of all, these set of four data are taken with the half-wave plate, and that generates linearly polarized light. So in the top row, the blue dots are measured data. So you can see that for linearly polarized light, most of the measured data are all physical. There are some non-physical points where the DOP is greater than 1 in the first two columns. So as you can see here, the corrected DOPs are all smaller or equal to 1. And from the Poincare plots, you can see that the corrected Stokes vector is in the same direction as the measured one, which is what we want. And because the measured degree of polarization is so close to 1 already, so the max DOP for everything here is just 1, and the minimum is just shifted here down a certain value. Oh, and I should mention that this was calculated using the Frobenius norm. So next we do the same thing, except replacing the half-wave plate with a quarter-wave plate to generate elliptically polarized light. And as you can see, for both methods, elliptically polarized light causes unphysical measurements more often. So, but the corrected results, same as before, the corrected results all have DOP smaller or equal to 1, and they are all in the same direction as the measured Stokes vector, as you can see from the Poincare sphere plots. Now there's two exceptional points in the first plot where the minimum does not have a solution, the minimum DOP. That is because the measured Stokes vector is too far outside of the Poincare sphere. And given the tolerance, well, I should say the minimum Stokes vector corresponding to this tolerance is still lying outside of the Poincare sphere. So the optimization problem does not have a solution in those cases. And that's what causes these missing points here. So, so finally, we want to compare our method to previous work. So namely the reference giving the footnote. So this paper was published in Applied Optics in 2013. So they compare, well, no, they look at two estimators, one which they call the empirical, and the other one is the one that they proposed. So first of all, the vector S here is just a column vector of the 4 Stokes parameters. And the superscript U stands for unconstrained, which is obtained from many intensity measurements. And that so the unconstrained Stokes vector includes all errors or noise in the experiment, which may or may not be physical. So they claim that what people normally do is what they call the empirical estimate is just to multiply S1, S2, and S3 by 1 over P, where P sub U is the degree of polarization of the original unconstrained Stokes vector, while leaving S0 unchanged. And they propose a different estimator, which they call a constrained maximum likelihood estimator. This was derived from the empirical one using a Lagrange multiplier method. And the Lagrange term that they found was this term out in front, 3 plus P over 4. As you can see, for both these estimators, if the unconstrained Stokes vector is already, well, no, if the degree of polarization for the unconstrained is already smaller than 1, these will actually change your measured Stokes parameters. Well, they will actually shrink the Stokes vector down. So in practice, to apply these estimators, you will have to separate your data into 2 piles, one that's already physical and one that's not physical, and you'll apply these only to the ones that are not physical. So the method that they use to compare between these is they look at the root mean square error, where X hat is the estimator under consideration, and X0 is the true value for different values of signal to noise ratio. So the figure to the right is taken from the same paper. And you can see here that for the degree of polarization, the empirical and the CML estimators give roughly the same error. But for the intensity, there is slight improvement in the CML method over the empirical method. Also keep in mind that these results are simulated results, and they use 20,000 samples. So next, well, the first thing we want to do when we're comparing between methods, we wanted to use the CML method for our experimental data. And these are results. So there's a lot of stuff going on in this figure. I'll go through it one by one. So this is one set of data out of the 8 sets of data that I've shown you previously. And the black circles are the corrected results from the CML method, the blue, purple, and green circles are the corrected results from the convex optimization method with different matrix norms. So looking at the S0 plot, you see that everything from the convex optimization is just 1. That's enforced by the trace constraint in the optimization method. But for the CML, the intensity is actually greater than 1. And that is caused by this. So I rewrote their CML estimator equation here. So you can see if P is greater than 1, the S0 of the unconstrained Stokes vector is multiplied by a number that's greater than 1. So it makes the corrected term greater than 1. Now for the S1, S2, and S3, it looks like that all the circles overlap of different color, even the black one. So it means that the corrected result from the CML method matches the convex optimization method, even if we use different matrix norms. There's slight difference here, maybe that might be just due to numerical errors. So the other thing that we have here is we have the max DOP, the Stokes parameters corresponding to the max DOP from the convex optimization method, and those are the x's, the different color x's, and you only see one color because they all overlap also. And this is because our measured DOP are all close to 1, so the max is basically the same state. Now there's a difference between the minimum value, the Stokes parameters corresponding to the minimum DOP, and those are given by the squares. So then we can see that there is a difference in the minimum DOP corresponding to different norms. So next, we want to look at the same thing that they did, which is the root mean square error. So the results here are simulated. The number of samples we used is 50,000. So this is a simulated result where the true value is the diagonal state. So the diagonal state has has S1 and S3 equal to 0 and S2 equal to 1. That is the true value used in this simulation. So again, looking at S0, the root mean square error for S0 is 0 because, again, due to the trace constraint that the trace of the corrected matrices are all 1, so the error is just 0. But we can see that the convex optimization method has a marginal improvement, I should say, over the CML method for the root mean square error for S1, S2, and S3. Now this is a different simulation where the true value is the anti-diagonal state. So the anti-diagonal state, the value for S1 and S3 are 0, but for S2 it's -1. So the results here is almost exactly the same as the previous one, which is expected, because it's a diagonal and anti-diagonal state. And so we did notice that the CML method does not require pre-normalization, and our convex optimization method does require that. And so this is not the full picture here, I should say. To get the full picture, we are going to not normalize the measure results and remove the trace constraint from our convex optimization methods and run this simulation again. And I believe that computation is being done right now. So hopefully we will have the new results like in a few days. So to conclude, we present mathematical method based on convex optimization for correcting non-physical coherency matrices measured in polarimetry. We also developed the method for recovering the matrices corresponding to the smallest and largest values of degree of polarization, giving tolerance. So our technique has the advantage that it's applied in post-processing, which does not require any prior information concerning the experimental setup, calibration of components, or specific type of experimental error or noise. So thank you very much for your attention. That's all I have to say today.
Thanks for your talk, Wenlei. Are there any questions? So I'll ask a question.
Sure.
You're talking about the connection between qubit state tomography and polarimetry. So there are many techniques now for qubit state tomography. I think some of the most successful ones are these compressed tomography, where they can really reduce the number of samples that are needed to estimate the density matrix. It's very impressive, and it's useful as you go to larger numbers of qubits. So is it direct to use those techniques, or are there nuances that are particular to the setting of polarimetry where they don't necessarily apply directly? And if you already addressed that, I'm sorry about that.
No, that is an excellent question. Yeah, so that is the subtle difference between qubits and polarization. So you can think of going to like higher dimensions, but what does that mean for classical optics and polarization?
Yeah.
Yeah, so for polarization, it's really just 2x2 matrix. So I don't know if we actually do get the advantage of the methods that work for high dimensions, for large dimensionality. So,
well, for your method, you do have to do repeated sampling, right, to arrive at an estimate.
Right? For the simulation, yes, but for these, yes, these are repeated samplings over like thousands of samples. But what we are considering is like for here, like you have a one-shot measurement where, like for example, a single photon, the photon is lost upon measurement into the polarimeter, and by some chance you get a result that's not physical, and you want to correct it, but the photon is already lost, so you can't repeat the measurement. So that is the one of the motivation that for our method is that you can do it in post-processing like that.
Okay. Peter has a question. Why don't you go ahead and unmute, Peter?
Yeah, I guess I'm familiar a little bit with these maximum likelihood things of like you run an experiment and then what you get is non-physical. In this particular thing, is your quote point estimate going to always be non-physical because of some sort of dimensionality thing? That was a problem we ran into once, is certain types of tomography is just you're guaranteed to get something unphysical because it's like the physical things are sort of like a two-dimensional slice through like a three-dimensional space, and your error bars go into that three-dimensional space. So do you always get something non-physical?
Well, I'm not sure, like if you look at the measured results here, the majority is actually physical. On
the
this
degree
slide.
of polarization, I guess, but
right. Well, we are, yeah.
Does it correspond to a like a valid like vector? Degree of polarization.
Yeah, the degree of polarization just represents the, like if the degree of polarization is smaller than 1, then it's definitely a positive semi-definite matrix. If it's greater than 1, that means it has negative eigenvalues.
Mm-hmm.
So that's why we're only looking at DOP here. If the DOP corresponds to the length of the vector in the Poincare sphere. So if it's smaller than 1, it's inside the sphere. If it's greater than 1, it's outside the sphere. So everything.
So if it's less than 1, it automatically corresponds to a valid.
To a physical, yeah, a physical density matrix.
So you wouldn't do this convex optimization, you would just
We could, but it will just return the exact same answer as you mentioned.
So sometimes you do get physical states. Okay,
Right.
I guess that sort of answers my question. I had a follow-up question. No matter what, these states that were sort of like outside of the Poincare sphere, is it literally like you're in this three-dimensional space in the ray corresponding?
Yes. Yeah. So
you can literally think about it being plotted like in
Right.
3 dimensions, like just a little bit outside of the Poincare sphere, and then
exactly.
Okay.
The Stokes parameters are just the coordinates in this 3D space.
Ah, I see.
Yeah.
So you said something like once there was some plot where you were like we were too far away from the Poincare sphere. And
for example, here this point, like it depends on the given tolerance. So we set the tolerance to be 0.1 here, and that if we are trying to calculate the minimum is still outside the sphere. So that's why.
Okay.
We don't get the answer here.
All right, I'm satisfied.
Gerard had a question. If it's brief, we could go with it. Do you have a question, Gerard?
Okay. I think you're muted.
I think I'm
sorry. Yeah, my hand was still left up.
Okay.
Oh,
That's good. Thank you, Wenlei, for the talk.
Thank you.
We should